Hi there, you are currently watching the accompanying video for the data preparation for injury prediction technical report paper. I'm Jovanovic, the author of this report, and I'm gonna walk you through this code and the sample dataset. So I'm currently in the R Studio, which is IDE, or the developmental environment for R language, which can be considered a lingua franca for data analysis and statistics in general. So if you don't have any, I would say, R background or R knowledge, you're probably gonna struggle a little bit. So, but I'll give my best to guide you through the code and what the code is doing. But I also urge you, as if you're someone who's working with the is working as a sports science in field and or researcher, to start learning or learn R language, because it's quite powerful, as you will see probably. So I'm gonna execute this code step by step, and I'll give my best to guide you through all the stuff involved in all the assumptions involved in this report. So just before I start, I need to quickly remind you that what we are doing with statistical analysis, we are creating a golems. So I'm gonna use the Richard McElrath example from his fantastic book called the Statistical Rethinking, where he actually mentioned this idea by I think it was Savage, the researcher or famous scientist, that we are trying to model the complex reality or the complex world, entitled a big world, into a small world, into a constrained set of assumptions that we can model statistically. So same thing here. So as you will see, we are having a lot of assumptions. We have a lot of ways that data can be, the complex reality of training will be represented in a data set. And we also make a lot of assumptions when it comes to removing the missing values or removing certain stuff, and so forth. So all these, including the way the data is represented, the way the data is cleaned, the way we deal with missing values and so forth, is the part of the overall injury prediction model and the part of the assumptions inside that model. And for this reason, I'm a big proponent of the open science or the reproducible science, where researchers are sharing both the code and the data set, so the same analysis could be reproduced by the other researchers. And in that way, the things are much clearer. For this reason, I made this video to showcase one way to kind of model this complex reality that the data we collected in real life, in real training, how I aggregated, how I analyzed it. And I also wanted to share both the code and the sample data set, so you can reproduce it and improve it and so forth. So without further ado, let's get started. So the first thing I'm gonna do, I'm gonna load the needed libraries, and there are two functions that I'll walk you through as well. But just don't get hung up too much on these two, especially the second one. So the first one is used to calculate the acute to chronic workload ratio, and it just tries to avoid dividing by zero. Sometimes the chronic, as you're gonna soon see, sometimes the chronic is equal to zero. So if we create a training stress balance or acute to chronic workload ratio, we ended up dividing by zero, and this ratio ends up being infinitive. So this function just protects from that case. And again, it's also part of the model itself. So if the chronic is zero, then return zero, otherwise return the ratio. The next function deals with extending the injury tag, and I'm gonna walk you through that in a second. So just gonna execute these so the functions are available for the rest of the code. So the main part of the code, so we're gonna load the data set, and again, this is a sample data set, and I'm gonna walk you through how the data is represented. So the data from the complex domain of the big world of performance is represented in this simple data set. So here we have 3 athletes tracked daily for one season. So we have a preseason and in-season inside this data set, and we have 3 athletes that suffered certain injuries. So as you can see, the first assumption is how the data is represented. In this case, the level of analysis, I would say the unit of analysis is a single day. So rather than a week or a session, we have a single day. So each row represents a single day. Here we have multiple columns. So there are first few columns are the I would say identifying columns that identify the certain period. So the first column is a column that's being used in the predictive analysis, where we separate 2 splits. So one is a training data set, the data set that's used to train the model, and the next one is a testing data set, which is not covered in this video anyway, but we are using that column to kind of split the data to be used in estimating the predictive performance of a given model. So the season number, it could be date, could be number. The phase, so it's a preseason or in-season or off-season. The date, in this case, represented, or it could be called a day, actually. It's representing I would say, the index of a day, so it's incremental. The player name, and we have 2 columns representing the injury. So first column is the injury location, and if you scroll down this data set, you'll see that these athletes suffer different injuries. So this athlete suffered the hamstring injury, and then the injury type. So it's a soft tissue injury. And again, the way we represent the injuries is also part of the model assumptions. In this case, we have few categories. I think we have a few locations. So it's probably the hamstring, groin, and the quads, and the injury type. So it could be a contact injury, could be soft tissue injury, or could be overuse injury. Again, depends on the way you classify the injuries happening. So for this model and for the injury prediction in general, we are mostly focused on the injuries that we can avoid. So, you cannot really avoid the contact injuries. I mean, that could be discussed, but usually we are concerned about the load-related injuries. So those are mostly overuse and soft tissue injuries that we want to predict, and at the end of the day, we want to minimize or prevent. So we are just tagging all the injuries that happen for this individual, and then we have 3 columns that contain the 3 variables that are that are proxies to training load. So we have RP load, which is a session RP multiplied the session duration. We have a total distance from a GPS, and we have high speed distance from GPS as well. Again, looking at these, we are already making certain assumptions. The first assumption is that what about for example, the strength training load, like the tonnage and so forth. So we are representing the complex reality with a simplistic a model, and in doing so, we are already making a lot of assumptions. And in this way, we are making assumptions that the gym load it's not included, and it doesn't matter for the injury prediction. So anyway, there could be a lot of metrics that you can implement inside. In this case, I only use 3 metrics just for the sake of example. It could be extended to include all the other external and internal metrics. And one more thing also worth considering, we can also, in this model, we can also include, say, a readiness metric such as wellness and so forth. But the problem with those metrics is that they are sporadically, or not really sporadically, but they are taken a few times a week, not every day. So we're going to have a lot of missing values for those metrics. And one way to deal with that is to, say, assume so for example, if we measure wellness on this day, but we didn't measure it until this day, we can assume that the wellness is the same across all these days. So we are pretty much populating the missing values for the wellness. Anyway, this is not included in this analysis, but it could be included. And again, the way we analyze it, the way we represent it, and especially the way we deal with the missing values, in this case missing days for the wellness, it's the part of the model. So anyway, this is the data. It's quite simple. We have three athletes, and they are organized in in rows. We have the identifier of the player. So this is just one, I would say, a neat and clean way to represent the data. Again, for the main part is that there are no missing days here. So there's no missing rows. And you can assume that for a missing row, there's a zero load. So if someone didn't have the data for a given day, you can assume there's a day off, so there's no workload. And again, it's also a part of the model assumptions. So this is the model. This is the data set, the sample data set. So because we're going to do a rolling averages, exponential rolling average, we can also add few extra missing, I would say, 0 days in before the data is collected. So pretty much to represent the off season without training. So again, it's an assumption. So I'm gonna generate the empty days, and I'm gonna merge. So these are the empty days. So I just generated up to -70, and I pretty much left this empty, and I assume the RP load, total distance, and high speed distance are 0. So I'm gonna merge these two data frames, and then I'm gonna sort it. So then you can see that for each athlete we start from -70. Just we give some zeros in the data set, so for the rolling average to do its job. I mean, you can do it without it, but you can, again, it's also a part of the model assumption. So the data starts at 1. As you can see, it starts at 1. So we assume that everything before is 0. This is done because we want to minimize the number of missing values, as you're gonna soon see. So first we need to create a long format. So the long format, I'll walk you through it. So the long format, as you can see, this is a wide format because we have I would say the variables of importance organized in columns. With the long format, we're going to organize them in rows. To do that, we need to have a identifier column that identifies which variable we are talking about. So the long one, as you can see, we have a variable and a value. So we have repeated variable, and this format is much longer, but this format is much better, and it's easier for graphing, it's easier for analyzing and so forth. So now I'm gonna, once we created the long format, I'm gonna create acute and chronic rolling averages. So I've used the exponential rolling average, and I'm gonna also create the lag in the chronic one. So to avoid the overlap between acute and chronic. So if you don't create a lag, then the windows of the acute and chronic will overlap. In this case, I've used the exponential rolling average, and I use this formula to kind of convert the days to alpha, which is used in exponential moving average. So I'm using 7 and 42. So 7 days for acute, and chronic and 42 for chronic. And I'm gonna create a lag of chronic for 7 days. So just to avoid the overlap. So lag is just shifting the cells downward. And we're gonna repeat this procedure later, so you'll understand what it actually means. And another thing I also introduce here is to get the previous week or the rolling maximum. So once I calculate the acute and chronic, I'm gonna get the acute to chronic workload ratio. So just a ratio between acute and chronic, but also to get some idea what might be the highest day in the last 7 days. So just gonna repeat that, and I'm gonna put that in the model. Again, there are a lot of ways you can do this. So this is just my personal way of representing the data and modifying the data. So I'll open the this one. So now we have acute and chronic for each variable, and acute rolling peak. So I'll try to sort this out so you can see. So let's say date, player name, and variable. So we have, day variable. So days are repeated in this case for each variable. And let's see when we start from 0. So okay, we have where is 0? Somewhere here. Okay. So we have for RP load. So this is the daily values, right, for one player. And then we have, okay, so this is the same thing, it's repeated column. So we have day values, we have acute, we have chronic. And as you can see, the chronic is shifted downwards. So the chronic is shifted for 7 cells downward just to avoid the overlap. So this is the ratio between acute and chronic. And this is the peak. So this is a rolling peak. So let's see 18 here. So that means, so what's the highest in the last 7 days? So for example, let's see 32, 32, 32. So in the last 7 days, the 32 was the highest acute to chronic workload ratio. So maybe, we have this, if you have one really hard day, or if you have one day when the acute to chronic workload ratio is high, we can repeat it across, it's like a history, just creating a memory inside the data set. So this is one way to do it. So it's what's the highest acute to chronic workload ratio in the last 7 days? So that's the acute to chronic workload rolling peak. So these are the main variables inside this model. So let's just do a quick plot. So it's gonna take a while to plot it. So I'm gonna zoom in. So we have this trellis plot. We have a RP load, total distance, and high-speed distance for each athlete. And on the x-axis is the days, and on the y-axis is the actual value. The red represent the acute chronic load or the acute rolling average, so 7 days rolling average, and the blue is the baseline or the chronic rolling average. So again, we are using exponential rolling averages, so you can see there's like a nice response to those as well. And it's I would say the plotting the data set is the first way to spot any potential issues. And as you can see, because we added leading zeros, they are visualized here as zeros or the period before 0. So we created 70 leading zeros in this case. If we haven't done that, we're gonna have missing values at the beginning of this data set, especially for the acute rolling, acute to chronic workload rolling peak. So we're gonna have missing values because we don't have any data set. So in this case, we filled it with 0, and we avoid having any missing values in the data set. So let's plot the acute to chronic workload ratio or training stress balance. And you're gonna soon see one interesting thing. So the gray one is the acute to chronic workload ratio, and the red one is the metric I just mentioned, the the maximum in the last 7 days, so the rolling peak. As you can see, it holds certain values, it holds the max. And the problem you can see here is the ratio is like really high here. So it's like over 1,000. So it means that the acute is 1,000 times more than a chronic. And this is usually happens at the beginning of pre-season, once you start collecting the data. And there are multiple ways to deal with that. The first way would be to maybe create discrete and discretize the metrics. So rather than having the continuous score, we might say it's over 1, over 2, and so forth, just to kind of cap these extreme values, because it can affect the modeling later on. Not sure that's the best way. Again, it's a part of the model, it's the assumption that becomes part of the model. But we can also remove a lot of data sets inside. So we can remove certain maybe first 40 days and so forth, don't include them inside the model. And again, this needs to be reported and needs to be, it's a part of the it's the assumption that's part of the model itself. As you can see, we see this issue with the high-speed distance. If you look at the previous graph, so we see here there's like a big jump in acute compared to chronic. That's why we have really high acute to chronic workload ratio that can affect the model itself, and we need to have a way to deal with it. Again, the easiest way is to cut the initial period, but what if the injuries happen in that period? You're going to cut those injuries from the model itself. And in our data set, the injuries actually happen in the first 40 or 50 days for the athlete 1. So this is the optional row. And again, this is why it's important to report all this stuff in the paper. And I would say the even better option will be to openly share the code and the data set, so for the other researchers to reproduce it and check all the assumptions. So anyway, I'm gonna proceed with the data wrangling. So I'm gonna proceed. So we need to, from this long format, we need to convert back to to kind of melt the data. So we have this one. So I kind of melted the acute, chronic, the ratio, and the rolling peak together inside one column. So this way we have a metric, the GPS metric, and the value, or the aggregated value. So you can see there should be, let's sort it like this, or sorry, date player. So I kind of merged together those three metrics we are measuring and the aggregation. So we combine them in one column. So the problem with all this, I wouldn't say the problem, but the issue with all this data preparation for injury and injury prediction modeling is, for example, what if we have a peak in acute to chronic workload ratio, or we have a peak in a training load, and the injury doesn't happen on that given day, but it happens maybe 7 days after or 14 days after. So it's like a delayed effect. So we need to have certain type of a memory, in quotation mark, in the model or inside the data set. And one easiest way to do it is to create a lag variables, similar as we did with the chronic variable itself. So with this code, I'm gonna create a lagging variables, and now you're gonna soon see. So I'm gonna open this one again, and I'm gonna sort date player and say, so in this case, based on a sort, we have high speed distance acute to chronic workload ratio. As you can see, it's 0. It's 0 up to, let's start from 0, from the day 1. So we have this ratio here, and the lag variable, it's just shifting stuff for 1 day, in this case downwards. So lag 7 is we shift this one for 7 days, lag 14 for 7 days, lag 21 for 21 days. In this way we kind of create a memory. So what if injury happened here, we need to check what happened 7 days before, or what happened 21 days before. So we kind of simulate, I wouldn't say simulate, but represent this delay of that might happen in a real world. So having a big spike, and then the injury might happen maybe a few days after, or a week, or even 2 weeks afterwards. So this is a way to, like, really simple way to represent this in the data set itself. So I'm just gonna continue with this, and then we're gonna merge this together again and convert it to a wide format, sort. So now we have everything sorted out. So monitoring data. Just gonna close this one. So now, if you remember, we have a column that identifies the metric, but converting to a wide format, we converted that each metric have its own column, and this way the data is again one day, one athlete per row. So you can see that we have again high speed distance acute to chronic workload ratio, and we have a lag variables. So we created a lag variable. So lag 0, it's the without any lag. Lag 7 is 7-day lag. Lag 14, so it represents what happened 7 days before, or 14 days before, or 21 days before, for all the metrics we have created. Anyway, now we need to decide which injury we want to, I would say, predict. So as I already mentioned, we want to predict all the soft tissue injuries. And again, the model can be built for example, predicting the quad soft injury, or hamstring soft injury, or groin soft injury, rather than pulling them all together as a soft tissue injury. I guess that maybe certain stuff will be more predictive of hamstring injury, for example, high speed distance, where certain stuff will be more predictive for a groin injury, for example, change of direction, and so forth. So if we clump them together inside the same tag, or inside the same model, we might get not really powerful model to predict the soft tissue injury. So in this model, in this example, I clamped them all together. So we are trying to predict any type of soft tissue injury, and again we can build multiple models to try to predict for different type of injuries or different locations of injuries. The problem is, of course, the lack of data. To predict the quad injuries, you do need to have quad injuries in the data set, and that's usually the problem because we don't have many occurrences. So I would say the solution might be to kind of organize multiple clubs inside the league to collect the data set for long term, maybe for a couple of seasons, and then try to build predictive models, and maybe split the models and try to predict for different type of injuries. Another major assumption in this model is that any other type of injury is not affecting the second injury. So for example, if I suffer the contact injury in my quads, that's not going to be represented in the model. So the effect of that is not going to be represented of the model. It's going to be independent. So if I get I would say the the maybe knee in the quad, maybe 7 days, that's going to be a contact injury. That is probably affecting the potential for, quad pull down the road. But in this way, the way the data is represented, that's not being implemented in the data or in the model. Again, that could be also represented using the lag. So for example, maybe is there any injury in the previous 1 month and so forth. So that could be also put inside the data set. So anyway, in this example, the assumption is that there's an independence between the injuries and injury types and injury locations. Okay, so now we have the data pretty much ready with and I think at the end here we have the injury and injury 1. So it means that it's just a simple yes and no. So it's set up so the data it's modeled using a classification algorithms. In this case, the athlete is either injured or not injured on a given day. So I think there's one injury here, or should be one injury. Okay, so here it is. So it's a bit slow. So he's injured on this day. So if you put this data inside the model, it's gonna speed up the likelihood or probability of getting injured on a given day, which I would say it's not enough, and it's gonna be only a few instances where we have this tag positive. So it's gonna be really, really unbalanced data set. So one way to deal with that is to create, I would say, I call it injury lead. So we want to see, we're gonna extend the injury tag for previous 7 days. So in a way, we extend the number of instances where someone is injured, but we also get I would say the warning light earlier. So in this case, we might get the probability. If we put this inside the model, we're gonna get the probability of someone getting injured in 7 or less days, or 14 or less days, or 20 or less days. So the function that I wrote before is pretty much just making sure that for a given injury, for a given injury column that we created, we're gonna populate the previous 7 days of the same tag. So I'm just gonna walk you through it. So I'm just gonna create these leading injuries, and I'm gonna reorganize the data set. So here we have the original data set plus the modified and prepared data. So we have injury location. So here's the injury tag. So if we find the hamstring injury, so here it is, should be here somewhere. Sorry. So hamstring soft tissue injury. As you can see, the injury 01, that means he's injured on that day. But the injury 07 means he's, it's a like we are trying to model this window. So, once we put this in the model, we want to see if someone's gonna get soft tissue injury in 7 or less days. And in injury 14 is 14 or less days. In 21, 21 or less days. And if we combine these, so injured, I'll call this injury lead, with all these lagging variables, then we might get this overlap between what happened 20 days before or 14 days before with potential for injury, and the model might be better at figuring that out. So it's a very, very simple trick to combine the introduce the memory inside the model. So as you will see here, there's going to be a lot of, should be few missing values because of the lag. And now the question is like, what should you do with all these missing values? So some of these missing values are because of, we introduced 70 days of zeros leading to preseason. But then also we might get these not zeros, but if you remove those first few days because of the spikes in acute to chronic, we also need to remove much more days because of the lagging variables we created, because the spike will be represented down the road as well. So the more lagging variables you introduce, the more data you need to remove, and it's like it's a trying to find a fine balance. With some predictive models, some of the machine learning algorithms can deal with missing values and some can't. So with some models, you do need to remove the missing values. So in this case, I'm just gonna leave them, or actually I'm gonna remove them, and then I'm gonna plot to see. So now we cleaned up the data set and we created the data set that could be used for modeling. And the easiest way to see if there's any association is to try to plot. So in this way, we're gonna plot and see if there's a difference between distribution, all these metrics we created, with the injury 07 or the injury tag where the soft tissue injury happened in 7 or less days. So I'm gonna plot these. Takes a while to generate the plot. So this is just a distribution graph. So we have a injured and non-injured, and we want to see if they ideally you want them separate. But in this picture, in this graph, you can see that there's a big overlap between metrics when the athlete is injured or when the athlete is not injured. So this is for all the metrics we created. As you can see from 3 metrics that we had, the RPE load, the total distance, the high speed distance, we created much more, we kind of engineered much more metrics. And I think it's 1, 2, 3, 4, 5, 2, 3, 4, 20 metrics. So from 3 we got 20, if I'm correct. 1, 2, 3, 4, 5, 1, 2, 3, 4. Yeah, 20 from 3. It's because we introduced the lag variables and so forth. And actually this is only RPE. So for one variable, in this case RPE, we get extra 20 variables. So we engineered 20 variables because we calculate the acute, we calculate the chronic, we calculate the ratio, we calculate the maximum in 7 days, and then we introduce the 4 lagging variables. So lag 0, lag 7, lag 14, lag 21. And ideally, you want to see separation between the classes. So you want to see separation between the distribution. In this case, there's not many. So this is RPE. Let's see total distance. So we're going to zoom in. So same thing, there's no separation between the classes. And you can immediately see that the injury prediction is going to be a bit tricky because there's no clear differentiation between injured and non-injured when it comes to these metrics. So this is similar to, I would say, single variable model, and ideally, as mentioned, you want to see a separation between distributions. So, for example, let's take the acute to chronic workload ratio. As you can see, there's no separation, and because we had those spikes at the beginning, we have this kind of skewed, and I would say the part of the model is how do you deal with those initial spikes when you have a longer period of zero training, or after off season, or when you start collecting the data? Should you remove that or not, and so forth? So as you can see here, there's just because we have these big spikes, we cannot see if there's any I would say differentiation between injured and non-injured depending on the acute to chronic workload ratio. So let's open the another metric. I think it's better because it doesn't have any spikes. So quite similar here. Ideally, you want to see, when the, say, acute to chronic workload ratio is, higher than 2, you're going to have more injuries than when it's not. As you can see here, it's not the case. At least it's not that easily identified. This is like this. Now we visualize stuff, using one metric, but we group them to RP, total distance, high speed. What we can do is to kind of combine them into one graph, and usually we use multidimensional scaling or PCA, or principal component analysis. We try to squeeze all this information in 2 components. So it's quite similar to a factor analysis, but it's really usable for plotting. So we are trying to squeeze the information from all these variables, and I think it's 60 variables if I remember correctly. So we have 3 types of variables: RP, total distance, and high speed, and we engineered 20 metrics. So 20 times 3 is 60. So we try to squeeze information from these 60 variables, in this case, to 2 variables. So we use a principal component analysis. So I'm going to execute that, and I'm going to plot it. So here we have, I'm going to zoom. So here we have 2 principal components, principal component 1 and principal component 2, and the injured and non-injured are colored. So we have a red is injured, and non-injured is this blue-green color. So ideally, you want to see clusters. You want to see these 2 classes separated, at least with, I would say, with these 2 components. There are 60 principal components here as well, but the first 2 contains the most information. So ideally, you want to see them, separated. And as you can see here, they are not really separated. So you cannot distinguish clusters between injured and non-injured. So just by checking these really simple descriptive, I would say descriptive, or visualizing the data in these 2 ways, you can see the injury prediction is not going to be easy, or we cannot figure out who's going to be injured from these metrics. So anyway, I'm going to save this data set, and in the future and in the next technical report or a paper, I'm going to walk you through how this can be actually used to create a predictive models. Anyway, thanks for watching. Make sure to download the code and execute the code yourself. The code will be available at the GitHub, and the link will be inside the technical report article. One more time, this is Mladen Jovanovic, the author, and thanks for watching. And again, please be free to contact me on the provided email and Twitter account.